All right. Um, Hello, everyone. Thanks for joining my session on extending Kubernetes. Our implementation on L4 Ingress controller. I am Srinivas Brahmaroutu. I work as a software engineer at IBM. I'm excited to come to Bangalore to give this talk and meet you all. I'm told that if you have questions on the session, we can meet outside after the session and discuss. The original presentation of this implementation was given in KubeCon 2018 in Seattle. We both developed the application. Wei Huang, he is now the chair of SIG scheduling. And I actively participate on Kubernetes conformance program as well as SIG testing and SIG storage. I've been working on open source projects for 4 or 5 years now, and about last 2 or 3 years on Kubernetes. To give you a big background on this, how do we expose the Kubernetes workloads externally, especially for L4 services? And the background and motivation for why we ended up developing this solution. And we introduced a concept called shared load balancer, which is a CRD and a custom controller, which is the way to go nowadays. And I'll show you a few demos on different cloud providers how this is done. Workloads are nothing but a set of containers running inside Kubernetes pods. They can communicate within the cluster using their internal network, but they cannot communicate to outside world. And in order to facilitate the communication, we have a resource called service. Services are of 2 types, right? Internal services, which are of service type cluster IP, and external services, which are of type NodePort or load balancer. Cluster IP service exposes the service on a cluster internal IP. Choosing this value makes the service only reachable within the cluster, but not outside. Our main focus today is to provide the connectivity for all our clients outside of the cluster. So let's see what a NodePort service is. A NodePort service opens a port on the nodes of the cluster, and when the client wants to connect, it needs to know the public IP along with the port of your service to reach your backend applications. So the port ranges 30,000 to 32,767 is allocated for, and all the workers should have a public IP and open these ports in order to communicate. The other option is service type load balancer. When you create a service type load balancer, it's actually the service provider who knows the best of their network setup and whatnot, and they'll create a load balancer for you, which is external to the cluster. And that's a public IP you use to connect to your NodePort service inside the cluster. This is the best option. And using this option, you should be able to connect a workload running inside the cluster through the load balancer to your external client. Again, this is very dedicated in the sense that each of your applications running inside the cluster will end up having a load balancer that cannot be shared by different applications inside the cluster, which causes some of the problems that I talk about today. And briefly, I want to touch upon the Ingress. Ingress Object is native to Kubernetes. And with the Ingress Object, we have shared connectivity at L7. HTTP headers have a lot of information, and using the subpaths, we can allow sharing and routing by setting up rules on the Ingress object and have the Ingress controller process these rules and send your traffic to different applications that are running inside the cluster. Ingress is a deployment model. It can be run as a daemon set. Ideally, there is one external load balancer, like I show here, that connects to the Ingress controller, which processes the rules so that you can connect to multiple applications. The advantage with this is there is less configuration, less resources to manage. There is only one load balancer. You can also have multiple Ingress controllers running inside your cluster by defining various classes of Ingress objects so they can act upon a certain set of classes. Popular Ingress controllers are like Traffic, Nginx, or Envoy, and it's useful for L7. So based on my brief introduction to services in Kubernetes, what you see here is a quadrant. A simple NodePort or load balancer service for L4 or L7, they are dedicated. Each application requires a service, and the service is one-to-one correspondence to an external IP. With the Ingress, you can share L7, but there is something missing here, which even the upstream wants, that is sharing on the L4 side. This is not a hypothetical problem we ran into. That's where our background and motivation is. We have an application that we wanted to bundle, and the application had several individual workloads inside. One for two JDBC connections we needed to connect to databases, and a UDP to transfer data, and then a web console. What happens here is that when you try to deploy this application, we end up creating multiple load balancers. That is not an efficient way for us to manage. What I wanted to do is, as you can see here, if I deploy an application, for instance, 4 of the applications, I want to have a single external IP with multiple, each of the applications have their own port. To achieve this, we wanted to share the load balancer that the cluster service provider will create for you. The way we can do that is if we can create a port for each of the services, we can use that port to delegate the traffic to individual NodePort services running inside the cluster, such that we can talk to different applications. This way, it is cost effective. We are using less number of resources. It's also user friendly. You don't have to remember much. There is only one external IP of the load balancer, and much better to operate on. And we can use the well-known ports of the applications that we can expose to outside world. And we are using the Kubernetes assets. We are not reinventing anything. Only concept we had to introduce is a shared load balancer, which is a custom resource object. It is exactly almost similar to a service definition. If you look at the spec of the service, it's nothing but SLB has to send that information back to create the services. So all we need is similar to a service spec. The CRD is similar to that. If you break down the problem now, as I described in the last 2 slides, you need to open additional ports on already deployed load balancer. And of course, you set all the security groups on Amazon or firewall rules, forwarding rules, whatnot. And then associate this to the backend pods. So all these ports that you're creating on the load balancer has to be able to talk to the backend pods. And how do we delegate that information back to the end user? Because he does not know what I did on the load balancer. The way we implement it is using a custom resource, which I call it shared LB sometimes, SLB sometimes, so bear with me on that. A custom resource object, when it is created, it creates a load balancer type service, which means that a load balancer is created for you. And to create the load balancer, we create with a dummy port, 3333, whatnot. You see it in the demo. And once we create that, we read the spec of the custom resource object, use that to create a port, like in this case, port A. And that port A is associated with the NodePort service inside the cluster. Now we have the connectivity into the cluster to talk to the application we want. The last step is whatever the NodePort services we created, we need to transfer the information of that back to the custom resource object, store it in there so that when the user queries, he knows exactly what is the IP and the port he needs to connect to. This way, you can share multiple L4 services through a single load balancer. Let's see some demos that will probably give us a little more insight into. So this is Google Cloud. There are 3 nodes that are running. Oh, sorry. Give me 1 second. All right, we are running a Google Cloud, inside a Google Cloud with 3 nodes running. The version of the Google Cloud server is 116. So we, like Dim said in the morning, we have all the new CRD definition validations and whatnot, and plus the new controller runtime. There are no services running. And I deploy 4 applications on this cluster. And when you say get CRDs, there is a shared LB CRD already created. And if you see the instances of shared LB, there are none. At this point, we want to connect to all these 4 applications, so we create 4 instances of the shared LBs. Each of them have the information how to connect to those applications. This triggers us to create 1 load balancer, only 1, because our capacity of the of this particular application is to run 5 connections on single load balancer by default. So if you look at the GCP console, there is only 1 load balancer created at this point in time. And on the front ends, if you see, that's the dummy port I'm talking about when I created the load balancer type. And as the applications shared LBs are created, they are getting all that loop is happening. The NodePort service is created in the cluster and the assignments are happening. So all the 4 services are having the same external public IP, and the ports are mapped. There is a 4001 port that is mapped to a port on the load balancer. Now, if you see, there are 4 front-end ports that are created for you that will be able to talk to the back-end NodePort service to connect to these 4 applications. And we have to create some firewall rules to open up the ports. So we, by default, open up all the TCP and UDP ports from 30,000 to 32,767. And there is only one external IP that we are buying. So the load balancer is set to use an external IP and set up forwarding rules so that the traffic can go through. As you can query the shared load balancers, they all show you the name of the load balancer as well as a port. So now if I do a netcat on these, I'm able to access all the applications that are running in the back. Let's see a different approach now on IBM Cloud. I want to see if my TCP and UDP services work. Again, like I said, load balancers are specific to individual cloud providers. They have different quirks or whatever you call it. So again, on IKS, I'm running 116. And I have 3 nodes. There are no services running at this point. And let me create 2 deployments. One is TCP and the other is UDP. Let's see the CRD definition. CRD definition is already uploaded into the cluster. So we can create the CRD objects. I am going to create one. Like I said, here I show the service definition of the CRD object. The port is 4001 for the TCP connection and 5001 for the UDP connection. Once I create the TCP shared LB, at this point that triggers me to create a load balancer on IKS. As you can see, get service shows you a load balancer created with a public IP. And the same IP is associated with my shared LB object also. Apart from the default port 333, there is also 4001. And if you look at the shared LB, the 4001 is associated with that. Let's create the UDP service. Now, both the services are going to share the same load balancer again and the same IP, but a different port. If there is a port conflict, what we do is we create a new shared new load balancer and use that load balancer for that port. So no worries about port conflicts. Let's do an echo test for the TCP and UDP with a -u option. So we did an echo test onto the application. So let's look at the application logs. The TCP log shows you the echo test worked fine, as well as on the UDP, we saw the echo test works fine. You can set the capacity of how many shared connections you want on the load balancer. One other cloud service provider that I would like to show you is Amazon. Oh, by the way, I'm also showing in this demo another random port assignment. So if you don't specify the port, a random port is assigned. So in this case, I am setting the capacity to 2 on Amazon. Let's run it on Amazon. Amazon is still, you can only deploy 114. So you don't have all the goodies that CRDs brings with 115 and 116. There are no services running at this point. I want to do 3 applications. Since I set the capacity to 2, eventually I'll be triggering how many load balancers? 2, because we'll run out of connections on the first load balancer. Shared LB definition is already in there. 3 deployments are created. By the way, the solution is namespace centric, so you can apply it to a multi-tenant environment. Again, I'm showing you what the shared LB port should look like. 4001, I created a shared LB. This triggers a creation of a load balancer on Amazon, as you can see in there. And there is a dummy listener as well as port 4001 for the first application. And we also have to create an Amazon security groups. So if you go into the details and click on the security group, there is a forwarding port on that security group that needs to be set. Inbound rule 4001. So we're all good. So we can connect to the application. Amazon, of course, uses CNAMEs to resolve, and that is my first shared load balancer that is created on Amazon with a dummy port. And then I have my shared LB, which has opened a port 4001. If you look at the shared LB, it shows me the definition slightly differently because we are using 114. We can do some magic with the output to see in a much more concise way. So shared LB1 is connected to that load balancer at port 4001. Let's create the second one. What happens? Our capacity is 2, so that means we can still share the first load balancer. So the second shared LB will still use the first load balancer, and we will get an association pretty soon with the same load balancer. As you can see, the CNAME remains the same, and new port is 4002. Now we create the third shared LB, and now we ran out of capacity, which triggers the loop to create another load balancer on Amazon for us, on EKS, I mean. There you see the second load balancer is created with a dummy port 333. And the third shared load balancer will be associated with that. The first two are to the first one, and the third one is. So at this point, what happens if my first shared load balancer is deleted? I'll still have 2 load balancers because I cannot rebalance the traffic. At this point, we don't have any solution to rebalance. So as you can see, the load balancers are updated, the listeners are updated, security groups are updated. You can see the second load balancer is using port 4003. First one is using 4001 and 4002 to connect to all my 3 applications. And if you go check the security groups are also updated accordingly. With the inbound rule set for those 2. NS lookups on those CNAMEs will work because it's an external load balancer. We can resolve it. And a netcat onto the first application works fine too. Let's delete one of the shared load balancers. So at this point, nothing else will be done. The load balancer, both the load balancers will remain because there is at least one shared applications still connected to them. Only thing that changes is the rules change. Because the 4001 application is deleted, we clean up those things. In the interest of the time, since I'm running out, let me go back to here to wrap up. I would like to discuss more about the design and implementation. Essentially, we used existing resource objects from Kubernetes. Only thing our controller does is manage the objects using the Cloud SDK to add ports and security groups or firewall rules, whatnot. N is configurable, and we create load balancers on demand, and we use well-known ports on the application, so it's a lot easy to connect. There are some differences on the cloud providers that is listed here on the slide deck. You can go through them. All in all, the most important thing I want to say is our code is on GitHub. Please do check out our code, and if you want to better our solution or make some changes, you wanted us to make some changes, just communicate with us on GitHub. Again, thanks for listening to me. Any questions, I'll take it outside. Thank you.